very important. And so they need to be confirmed or justified more fully. And so the purpose of this talk is to derive for you and show how it is derived the full force of gravity and also to show more implications of the force of gravity than we used in the previous talk. Implications in astronomy, implications that cover the largest phenomena in all the universe that we see. So, and there's a lot of them that have to be there if this model is true. So I'm going to try and cover that in this presentation. This, again, is the same picture we had before. We have the force of gravity is between vibrating neutral electric dipoles, and these exist in all atoms of material. They may also exist within an elementary particle, but we haven't had the need to try and calculate it, but we believe that you have plus and minus charges also inside an elementary particle, and you can have a dipole oscillation. So it is possible to have something like the force of gravity between elementary particles if they involve two signs of charge, two different strings of opposite charge. Okay. Reviewing a little bit here, this is a picture of Poincaré and his logical criteria. Again, he indicated that the force of gravity appears to be electromagnetic in origin. If we look at the structure of the force of Coulomb's electric force and also of Newton's universal law of gravitation, they are very similar. They both involve a constant, something associated with one body and something associated with the other body, and the distance between them. And so here we have G in place of that, and then we have M1 instead of Q1, and M2 instead of Q2, and we have the R12 squared. And Poincaré said that if the force laws are the same, then they are due to the same fundamental force. That each fundamental force has a unique form. And so that was what he said. So that would indicate that the force of gravity should be of electrodynamic origin. Now, another important person was Lorentz, and he had the first known force law that gave a correction to the Coulomb force law for static charges. And this is the force is equal to Q times E, the electric field, plus V, the velocity cross the magnetic field. And when you write everything out in terms of E, you get that the force is equal to QE times 1 plus V squared over C squared. So this first term here is just the Coulomb force. So this is the first correction term to the Coulomb force. It's V squared over C squared. And if you use the electron drift velocity in materials such as a metal, you see that this comes out to be approximately 10 to the minus 20 as a number. And if we look at the strength of gravity compared to the strength of the Coulomb force, it turns out it comes out to be 10 to the minus 40. And it suggests that gravity may be the next higher order correction to the Lorentz force law, V to the fourth over C to the fourth. It's the right magnitude. We don't know about the sign, but it's the right magnitude. So that was the background then that people thought of. And 150 years ago, most scientists thought that all the universe was electrodynamic in origin, including gravity. That's what they thought. We derived, and it's on the CD that I've left here, the universal force law. It comes from a scalar potential, and this is the force law including acceleration terms. This shows where F equals ma comes from, this term right here. This term over here handles radiation, emission, and absorption. Those are things that previous force laws do not handle inherently. It's an ad hoc calculation to handle that. And the next term, which we have not fully derived yet, but we're working on it, is the first derivative, dA over dt, which is a radiation reaction term. And we will be the first to get a legitimate derivation of that. The quantum electrodynamics community has tried through multiple international conferences at Caltech, and they have not succeeded in being able to derive that term from special and general relativity theory. So we will be able to do higher order terms than those other theories, and presumably we'll be able to explain more phenomena than any of them can explain. Okay, so now if we just look at the velocity terms in this, because the acceleration terms are not going to contribute to the force of gravity, they're going to contribute to the force of inertia. So if we just look at the velocity terms, then we have this scalar potential, and we have these terms, and we need to take them into account. So we're going to have a radial term here, and then an R cross V term coming from that part. If you look at the covariant Maxwell electrodynamic force, this is your E field, and this is your B field, and you can form, using the Lorentz force law, the force, and you get the same force law that we have. This, you can rewrite it and get it into this form. So the force law we have just through the velocity term is in agreement with the competing theory that we are working with, but it's derived with totally different assumptions. They're using point particles. They're assuming there's no feedback or finite size effect. We are using finite size particles. We're taking into account the feedback effect, and we're not using any of the assumptions of relativity theory. So we have two diametrically opposed theories that produce the same mathematical formula from which we're starting. And so here is the question of which one is true, and it has to do with assumptions. Yes, sir?
Your field does show a 1 minus v squared over c squared term. Is that not coming from relativity? If so, where did it come from?
No, it comes from in the derivation, which is on the CD, which I'm not going over, but I have the PowerPoint presentation on this PC actually. In that, the Lorentz, or the Lenz's force law causes you to get an iterative equation. And that means there's an infinite sequence of terms. We sum those terms with the binomial expansion, and that's what produces these denominator terms. The summation of an infinite series sums to 1 over 1 minus beta squared sine squared theta. So the terms are 1 plus 1/2 beta squared sine squared theta plus all those terms that this would be if you expanded it in a power series, in a binomial series. So it's the iterative equation, which is basically the finite size of a particle impressing itself back onto the particle through infinite orders of impression. In other words, there's a feedback effect. The field that the particle has when it moves changes the shape of the particle, and that causes another effect, which causes another effect. And you add up all of those effects, and that produces the same effect that relativity has, but relativity has a totally different mechanism and idea, assumptions for doing it. The assumptions we use are, as far as we know, all accurate. We don't know of any that are invalid. I pointed out 7 assumptions that were invalid with relativity theory. I pointed out there are logical inconsistencies in the theory because so we don't have that. But I want you to see that that result is the same. So I could go from relativity theory and calculate the force of gravity, completely independent of all the rest of my work. You don't have to believe in that to do that. Okay, so what we did is we we have to calculate. We know that the magnitude of the force is relevant for a beta to the fourth power. So what we did is we expanded this force to have all the terms up to beta to the fourth. And if you get my paper, this is many steps, multiple pages. I do every step, so you can follow it mathematically. The editors of journals hate my papers because they said, you shouldn't put all those steps in. Let people figure it out for themselves. And I said, well, no, this is a very important paper. I want everyone to know all the steps. So if you read that, you'll see all the steps. And you can check my math at every stage, which is the way I think it should be. Okay, so we have formulas here now. We need to evaluate that somehow. So when we come back to our model, we've now got our vibrating electric dipoles. We break the total force up into 4 pieces. In other words, the force between this piece and this piece, the force between this piece and this piece, and this piece and that piece. You know, we go all around, do all the combinations, and there's 4 of them. So we've got 4 forces that we must calculate, and we know the oscillation part is taken care of by terms like this, which show the oscillation. Now we get to the we have to do a lot of averaging. We average over time, we average over phase, and we average over the angular dependence. So these are our 4 forces that we've written down explicitly. You notice some of them don't have the amplitude of oscillation in the denominator, some do. And then we assume that R2 minus R1 is much, much greater than that, so we can ignore those terms because we don't know what to do with them in the denominator. They're very small. But up here in the numerator, we don't ignore those terms. We keep the A's. It's only in the denominator that we drop them. So we've got to evaluate this integral with these 4 terms put in for F. So F now is the sum of these 4. Here's the sum. I've written them out explicitly so you can see all of the terms. And you see the amplitude and the frequencies and the sign with the amplitude or the frequency in it, and also the phase. So we've got all of these, and we're going to have to average them over the quantities we saw in order to represent what we actually measure in the laboratory. So here's our formula. We now substitute all of those terms in here, and we take our average. And so the first term comes down, this is the radial term, comes down to this result, minus e squared over r2 minus r1 squared in the radial direction times a2 squared omega 2 squared a1 squared omega 1 squared times 2 over 5 pi. And we equate that, because it's the same form, to the force of gravity. And notice it has a negative sign in front. Everything else is squared. So it has to be only negative, only attractive. So we get a unique sign. And the other terms that were in the force that canceled out the regular Coulomb force and the beta squared terms, they all averaged out to 0. So we end up with just these beta to the 4th terms. So then you can generalize this for n atoms with z protons, and you end up with numbers like this. And now this can be equated to mass of an arbitrary body. So we can work with not just hydrogen atoms, but any size of atom, any type. The non-radial term is done in a similar way. We have 4 forces again. We must substitute in and average over those 4 forces. This shows how they're written out up to beta to the 4th terms, showing all the angular dependence and everything in them. And so this is the formula. We substitute in and average, and all the Coulomb terms sum to 0, and the beta squared terms average to 0, leaving only the beta to the fourth terms. And these can be evaluated down to this term right here. And if I use the same definitions I used to compare with Newton's universal law of gravitation before, I get 45 over 8 times g m1 m2 over r1 r2 squared times r12 dot beta and r12 cross r12 cross beta. So we get a new term which has never before been seen in the gravitational arena. It's not in Newton's universal law of gravitation, and neither is it in Einstein's general theory of relativity. So if I can prove that that term exists, I now have a proof that invalidates general relativity theory and Newton's universal law of gravitation. So that's what we're going to head toward.
What does that term do? I mean, why has it not been observed as a separate term?
It has been observed. It's been ignored. I'm going to use observed data to show that it exists.
What is it?
It causes a spiraling motion. In astronomy, it causes a spiraling motion. I will show that it exists on all size scales in astronomy. Yeah, we do. Okay. So when we finally evaluate all the terms, we get this for the force of gravity. If we try to identify it with previous theories, like Newton's universal law of gravitation, we end up with a term like this. And this is the usual gravitational form that would be compatible with Newton's universal law of gravitation, and then a relativistic version of that for general theory of relativity. This term is brand new. I identify that it's producing corkscrew spiral motion. And we're going to see that there's a lot of that. Okay, so now we want to look at evidence for this new theory of gravity. So this is a kind of a summary one, then we'll go through each of these items. Vibrating dipoles, the source of the force of gravity, have to radiate continuously. We're going to prove that the radiation is fully compatible with the 2.7 degree Kelvin cosmic background radiation. By fully compatible, I have to show that it's within the range and distribution that it could be for the physical situation. The second is the cosmic background radiation is emitted and absorbed with some radiation escaping. Okay? That's what we see at 2.7 degree Kelvin. But some of it doesn't. But the stuff that does escape causes the force of gravity to decline. The declining force of gravity causes the Earth to expand, and we looked at some data for that. It causes the Earth's angular rate of rotation to slow. We saw the data supporting that from the magnetic field data of the Earth. Also, I didn't say it, but ring lasers can measure the rate of rotation of the Earth and show that it's slowing down. And it can do it to many significant figures. In fact, the rate of rotation of the Earth is kind of jerky. It doesn't go smoothly, but you can take an average of it. So, and then, of course, the magnetic field decays. We can show that the moon recedes from the Earth. We can show that Hubble's redshift law is due to gravitational redshift. We can show that the rapid decay of Hubble redshifts over time is due to this decline of the force of gravity. And we'll get to that. Then the non-radial term causes a corkscrew spiraling motion of planets about the sun. It causes an effective tilt of the orbits with respect to the equatorial plane of the sun. And that is seen. I'll show that. It causes a quantization of the planetary orbits, which is the oldest known astronomical law for our solar system, called Bode's law. Bode's law, even though it's the oldest known law and it shows quantized effects in our solar system, has never been explained. It doesn't agree with Einstein's general theory of relativity, nor does it agree with Newton's universal law of gravitation. So it's considered a fluke in the standard textbooks. It also causes a quantization of the redshifts in the universe, a Bode's law for redshifts. So we'll get into that. Okay, the first thing we want to do is we want to look at the radiation that is coming from this oscillation. So what I have done is I've taken my terms that represent gm squared for hydrogen, where the Z is 1, you know, and so it simplifies the formula here. So I have this formula. I convert my omega frequency to a wavelength using the wave equation. And now I have the wavelength of the light in terms of the amplitude of vibration and assuming that this is a source of gravity, gm squared. So I can now solve for the wavelength that I would expect if the vibration of the electron with respect to the proton is the source of the force of gravity and it is radiating. I can get the wavelength I would expect. And for A, the amplitude of vibration, I would say that A has to be smaller than the radius of the atom. So in other words, the electron can't be vibrating so big it's outside the atom. It has to be inside the atom. So that is the upper limit. So lambda, when I solve for that and put in for all these values, their value, for lambda, it's less than or equal to 4 millimeters. Okay? That's calculated value. What do we see? This is the COBE cosmic background radiation that NASA has published, commonly called the T equals 2.74 degree Kelvin background radiation. Here is the 4 millimeter length. This cosmic background radiation is from all elements, not just hydrogen, but hydrogen is the majority of it. What we see is the majority is under 4 millimeters of wavelength, and it has the typical black body distribution, which we will get from our work. We've already calculated that and published it. So there's some that's higher, but there's helium, and there's other elements that produce some cosmic background radiation. So we say we have a perfect fit to the cosmic background radiation, and our explanation is more fundamental than any other. The Big Bang Theory does not have as satisfying an explanation for the cosmic background radiation. We have a physical phenomena that produces it, and it's fully consistent with the decay of gravity. Now, besides measuring that distribution, COBE satellite also measured the geometrical distribution of the cosmic background radiation. And so the density of the cosmic background radiation is reflected in these hotter spots and cooler spots. And these hotter spots correspond to where matter is located in the universe. So wherever there's matter, there's more cosmic background radiation than there is between places where there is no matter. So the cosmic background radiation is going around the universe in every direction, but it's a little stronger where there's matter. And that fits with our model. It's hard for the people who believe in the Big Bang model to come up with this fully a satisfied explanation of that. We've already shown the expansion data for the Earth. We can skip over that. Two different sources, both satellite and ship log records for sonar sounding. We've seen that diagram before, and that one, and that one. And we've seen the picture of the moon and its expansion data, and Jupiter's moon, and Europa and Venus. And here's a picture of Mars. And Mars has both oceans and seas that you can see in various places, but it's also got a giant crack. Some people think that something hit the other side of the planet and caused that crack. That might be a big meteor or something, but it also shows expansion. And we showed the decay of the Earth's magnetic field, the expansion of the Earth, and the change in distance to the moon. Now I want to get to redshifts. If we look out into space, the nearby stars have hydrogen gas around them, and the hydrogen gas absorbs part of the continuous spectrum of light. So we get, when we look at the spectrum, we get these lines, these black lines. These are absorption lines where hydrogen has absorbed a certain energy from the total spectrum. And so this pattern of lines is characteristic of hydrogen gas. When we look at stars that are a medium distance away from the Earth, we find that this spectrum has been redshifted. By that we mean the whole spectrum has moved to the right. And we look at things that are as far away as we can see, it's even further shifted to the red. And the first person who discovered that was a fellow named Hubble. We also have discovered at Princeton University that gravity causes a redshift. And the redshift is Z is given by the change in the wavelength of light over the wavelength of GM over C squared R. Now, we have said that in the past, the force of gravity was stronger and the items were smaller. Okay? So, it turns out that on the Earth today, the redshift from gravity is not as big as the redshift that we see in space. But in the past, when M was much bigger and R was much smaller, we expect the redshift to be thousands or tens of thousands of times larger than what we measure on the Earth today. Just due to the decay or gravity. We're seeing the light coming from planets in the past when they had a much stronger, or stars, when they had a much stronger gravitational shift. So Hubble was the one who first measured the redshift versus the brightness of stars, which is one measure of distance. And he found that there was a linear relationship. Hubble never believed that it was due to Doppler shifts. He was the discoverer of it. He believed that the Doppler shifts was responsible for the scattering of the data up and down, but not the main effect. We agree with that. Now, with regard to the motion of the planets about the sun, here is the sun. Here, this line here is the equatorial plane of the sun. The orbit of the Earth about the sun follows this, what looks like an ellipse. Okay? But that happens to be on the surface of a toroidal ring. Here's a cross-sectional cut, like a donut. I've cut the donut in half. Here's one half, you can see. This is the back part, and here's the other half. And as the Earth goes around the sun, according to this theory, it slowly goes around this cross-sectional circumference. And by the time it goes all the way around the sun once, it is going all the way around here once. If you just look at the resulting orbit, it looks like a tilted ellipse. But there's something unique about this ellipse, and that is the perigee and the apogee occur where this ellipse crosses the equatorial plane of the sun. In Newton's universal law of gravitation and Einstein's general theory of relativity, that would not be the case. But observationally, it is the case. So it appears that the spiral motion of the Earth on the surface of a toroidal ring is producing the actual orbit, and it predicts the point in the orbit. The nearest and the farthest approach to the sun are where it crosses the equatorial plane of the sun. And I'll show you that in a second. This is a graph showing the angular tilts of all of the planets. This is the equatorial plane of the sun down here. Notice that they're grouped. There seem to be a group here, and another group here, and one here. And these are multiples of one another. this angle here is twice that. This angle is 1 unit, this would be 2 units, this would be 3 units. And this stuff in here is what we call fine structure due to secondary effects. So we see that this data has never